Engine start. We have main engine start. 4, 3, 2, 1, 0, and liftoff. The liftoff of the space.
In our natural pursuit of knowledge, space has always mystified and beguiled us. Over the past 5 decades, we've pushed the final frontier inevitably onward into the ether. The cost has been colossal. Now every day, new data, new conclusions, and the thirst for deeper exploration propel us inexorably onward. The advantages of the discoveries made through space travel are myriad, but the fundamental curiosity as to what is out there will always fascinate and taunt us. Come with us now into the unknown and discover the disappearing frontier. In this edition, space research has led to some pretty invaluable spin-offs, such as the automated telemachine, a better bike helmet, and a cordless screwdriver. Where will it take us next? An efficient cardiopulmonary system is vital to our quality of life, and a deep breath in space may help solve the respiratory problems of people back on Earth. Laboratory safety precautions are important on Earth, but even more so in space, where a stray drop of water could fall upwards and short-circuit a vital piece of equipment. To explore the new realms of space required new materials to keep the explorers safe, and those materials have found applications here on Earth. A thin polyester film used on the Echo 1 satellite and then to line Apollo spacecrafts and suits was marketed as the space blanket. Spacesuit technology intended to keep astronauts from getting too hot is at the heart of the cool vest used by children born without sweat glands. The vest permits them to engage in normal activities without the threat of dangerous overheating because of their inability to perspire. And bicycle helmets are another spin-off from space research. The composite materials of many helmets worn by bike racers and pleasure riders are descended from NASA research on polymers and the aerodynamics adapted from airfoil designed to reduce drag on fighter planes. Even the bounce in the astronauts' moon boots are found in some types of tennis shoes, and abrasion-resistant coatings developed for space equipment are now used in scratch-resistant sunglasses. Can you imagine life without computers? They're anywhere you look today. While some developments in microcomputer technology are not direct creations of NASA research, the speed of their development got a boost from use in the space program. The technology used to enhance pictures of the moon is now at work in magnetic resonance imaging, and that with some astronauts' training program is today found in some flight simulator rides at amusement parks. And there's more on the way. Originally created as a flight experiment to grow large three-dimensional clusters of cells during space flights, the bioreactor provides an environment here on Earth where three-dimensional clusters of delicate tissue can be grown outside the human body. Samples which can be used for medical treatment of illness or injury and for medical research on such diseases as cancer or AIDS. An implantable device with just one moving part which assists a weakened heart until a transplant becomes available, or in some cases makes a transplant unnecessary. The method of preserving blood samples from astronauts in space is the impetus behind the dry blood chemistry method, which permits faster analysis of blood samples on Earth without the need for a bulky power-hungry freezer or centrifuge. And work on growing food in space has led to an artificial soil which doesn't need fertilizer, hence no runoff of chemical byproducts when you water your garden. The American space program, from its inception through the Apollo program to the space shuttle and beyond, has met the challenge while leaving a legacy of technology created for space, and it's developed by the private sector for our use right here on Earth. The next steps along the path are up to you. The space program provides a valuable insight into the functions of the body. For example, the cardiopulmonary system. Cardio refers to the heart, pulmonary to the lungs. This lung-heart connection is right in the middle of the cardiovascular system. Here's how it works. The heart pumps blood through our arteries and veins. The blood in turn has an equally important job. When the blood is on its way to our tissue and organs, it's said to be oxygenated, meaning that it's carrying oxygen to all of the cells in our bodies. When blood is returning from the cells, it is oxygen depleted, meaning that the oxygen has been used up and in its place is carbon dioxide. Looking at this diagram of the cardiovascular system, you'll see that it's a closed system. If this is true, then how does the blood get a fresh supply of oxygen to carry back to the cells? That's where the lungs come in. Oxygen-depleted blood is pumped from the heart to the lungs. When we breathe air, rich with oxygen, it enters the lungs. The oxygen in the lungs and the carbon dioxide in the blood are going to trade places through the thin membranes that line the lungs. This phenomenon is called gas exchange. On Earth, where gravity tends to pull blood towards our feet, the majority of blood in our lungs stays near the bottom and the air stays mostly in the top. But in space, where the fluid in our bodies shifts upwards, it's felt there would be a more even distribution of blood and air in the lungs. That means the lungs should function even more efficiently in space than they do on Earth. Space Lab's gas analyzers are going to help us to determine if this is true. By breathing into the rebreather device, we'll have a mixture of traceable gases. When we exhale the mixture, the gas analyzer will identify each gas and determine the quantity that was absorbed by the bloodstream. We'll then be able to determine if gas exchange in the lungs is actually more efficient in space. There are other valuable lessons we can learn from spaceflight. When we drink water or other fluids, the liquid goes into our gastrointestinal tract. From there, the water is absorbed into the bloodstream by a process called osmosis. The cells in our bodies then absorb whatever water they need from the bloodstream. The cells also dump water, along with cellular waste, into the bloodstream. As the blood passes through our system, it's monitored for different metabolic products. Two of our glands, the hypothalamus and the pituitary, monitor fluid levels in the blood. If the fluid level isn't right, the glands will release a hormone which tells the brain there's a problem. If the fluid level is too low, the brain tells us that we're thirsty. But if the level is too high, the brain tells the kidneys to eliminate fluid. Through an elaborate filtering process, our kidneys remove the excess fluids and waste from our blood and store it in the bladder in the form of urine. But what does this mean for the space traveller? Firstly, it means that when we enter weightlessness, the body fluids shift upwards and our renal intercom system will tell our bodies to eliminate fluid. What we don't know is how weightlessness affects the production of the hormones that keep our fluid levels balanced. Now let's consider the role blood plays in our body. We all know blood is essential for life, but do we know why? Blood has two very important jobs. First, it transports oxygen and carbon dioxide to and from the millions of cells in our bodies. Blood is also a defense mechanism that allows our bodies to fight infection and disease. Blood has three components: red cells, white cells, and plasma. The red blood cells can be compared to millions of taxicabs zooming around in our bodies. As each red blood cell taxi passes through our lungs, it's flagged down by an oxygen molecule. The oxygen is wanting to go to one of the millions of cells that make up our bodies. So the red blood cell takes off with the cardiovascular system towards that destination. Once there, the oxygen gets out and goes to the cell. Now, like any good taxi driver, the red blood cell doesn't want to make a return trip without a paying customer. So, while at the cell, it picks up a carbon dioxide passenger for the return trip to the lungs. Without red blood cells, our cells can't get the oxygen they need to sustain life. We all know that from time to time, foreign substances can enter our bodies. These substances might be bacteria, viruses, or even something like a splinter. That's where the white blood cells come in. The white blood cells can be likened to a good watchdog. When something or someone threatening comes to our yard, our watchdog will attack it. The white blood cells work the same way, except there are millions of them. When a foreign substance enters our bodies, the white blood cells attack and repel the intruder. But to carry out their tasks, the red and white blood cells rely on the third component in our blood, plasma. In the red fluid called blood, cells make up about 40 to 45%. The rest is plasma. Since plasma is a fluid, it's significantly affected in space by the upward shift of fluid in our bodies when we encounter weightlessness, and that affects the overall blood supply. As we learned before, when the fluid in our bodies drifts upwards, sensors in our system send a message to the brain saying there's too much fluid. And remember, the brain then tells the kidneys to reduce the fluid volume. Once the fluid has been reduced, the blood cells make up more than 45% of the blood supply. In other words, our blood becomes thicker. To compensate for this, we think the bone marrow decreases its production of red blood cells until the ratio returns to about 45%. So once again, our bodies adapt to the changes of spaceflight. But when we return to Earth, we face another problem. We find we've lost both blood volume and red blood cells. The loss of blood volume is a problem immediately upon returning to Earth because Earth gravity is pooling blood in our legs, and the decreased volume makes it difficult for blood to be pumped to our brain. This can lead to lightheadedness and a woozy feeling right after landing. We begin working to correct this problem even before we land by drinking lots of water. By drinking water, we begin to replace the plasma in our blood. The lack of red blood cells is called space anemia, and this continues back on Earth until the body manufactures enough red blood cells to bring the plasma cell ratio back to about 45%. Throughout every space mission, blood is taken from the crew, and these specimens are later studied closely back on Earth, so that we may learn even more about the behavior of bodies both on Earth and in the weightlessness of space. On Earth, gravity is a key force in the development of muscle, but in space, where there is no gravity, scientists must develop ways of preventing the astronaut's bone and muscle wasting away. Most structures are designed with a specific purpose in mind, the orbiter to cope with the unique conditions in space. Our bodies were designed to function on Earth, where there is gravity. In fact, our body's musculoskeletal system needs gravity to function properly. By pulling against our bodies, gravity makes our bones and muscles work and become stronger. Each time we take a step and push our weight forward, we perform a weightlifting exercises for the muscles in our legs. Activities like climbing stairs make our muscles work even harder. But in space, nothing has weight, so our muscles don't have to work the same as they do on Earth. When muscles don't work in their usual way, they become weaker. Most of us know someone who's broken an arm or leg and had to wear a cast while the bone heals. While in that cast, the muscles of the arm or leg didn't have to work, and once the cast was removed, that muscle was weak. The same is true for people who've been confined to bed for a long time and couldn't use their muscles. In space, astronauts use their muscles on treadmills and exercise bikes, but the results still aren't the same as they are on Earth. Imagine that every day we lift a barbell that weighs 100 pounds. Then one day we go on a trip that lasts a month, but we only have a 40-pound barbell to take with us. Even though we lift the 40-pound barbell every day, the 100-pound barbell is going to be hard to lift when we return from our trip. The same is true about spaceflight, depending on how long the astronaut is in space. It may be weeks or even months before he or she regains the strength in the muscles that's been lost. It could be even worse for astronauts who will someday live on the space station or on lunar bases, not to mention a trip to Mars that could last a year or more. Muscles aren't the only parts of the body to suffer during spaceflight because of weightlessness. In our bone are two types of cells, osteoclasts, which get rid of old bone matter, and osteoblasts, which build new bone. Because of the activities of these two cells, our bones are in a constant state of tearing down and rebuilding. The balance of these two cells seems to be tipped slightly in favour of the osteoblast cells. That's why our bones grow stronger. But what happens in space is still somewhat of a mystery. Since there is no weight in space, there's no stress on our bones as they go through the rebuilding process. This seems to affect the structural integrity of the bone. Bone density recovers, but without stress, they may not grow as strong. The only way to test the theory is to remove the bone, and so far there have been no volunteers for that course of action. So NASA is working on ways to test bone strength without removing the bone. Finding a way to test bone strength is going to help people on Earth who suffer from a common problem known as osteoporosis. From a spacecraft, the view is spectacular, but most of the time, visual reference won't be enough to tell if the craft is flying in the direction it should. For that reason, the shuttle has guidance systems. And we have a guidance system in our bodies too. It's called the neurovestibular system, and it's what keeps our bodies in the proper orientation on Earth. The neurovestibular system is very sensitive to gravity. In fact, it's gravity that makes it work. Deep inside our inner ear, in the vestibular organ, are thousands of tiny hairs. Resting on top of these hairs are microscopic clumps of crystals called otoliths. On Earth, gravity pulls the otoliths in different directions according to the type of activity we're doing. This in turn bends the tiny hairs, sending messages that tell the brain before hanging upside down, accelerating, or any other sensation that has to do with body movement. The neurovestibular system also uses sensors in our muscles to determine sensations of motion or changes in position. But most of all, it relies on our eyes. We might even say the neurovestibular system's main purpose is to create a stable platform for our eyes. When our eyes can't lock onto what we're looking at, we can get a queasy feeling we call motion sickness. It's the same feeling some people get when they take a wild ride in an amusement park. Everything rushes by in a blur. Some astronauts experience the same feeling in space. It's called space motion sickness. That doesn't mean riding a space shuttle is the same as riding a slippery dip at a carnival, but it does mean spaceflight can confuse our neurovestibular system and disorient the visual references we rely on for stability. There's a reason for this. When we get into space, gravity no longer pulls down on us the way we're used to on Earth. Things start to float away and, for all practical purposes, objects become weightless. In this environment, the vestibular system functions differently than it does on Earth, and we no longer have a way to tell our brain what the right body position is. Without the vestibular system functioning the way we're used to, some astronauts can get confusing signals in the brain. The eyes tell you your feet are off the ground, but the vestibular system doesn't give you the sensation of falling that you would expect. Usually, after a few days in flight, the body adjusts to the weightlessness and the space motion sickness goes away. However, until it does go away, it's quite difficult to concentrate on an experiment if all you can think about is how sick you feel. To help us learn more about space motion sickness and how to deal with it, these astronauts carried out some experiments in space. This experiment involves the use of the rotating dome. The dome helps us to see how visual cues affect the way our body responds. To do the experiment, the astronaut puts her head in the dome and looks at the dots as they rotate. Her eyes naturally want to look onto the dots. This causes her body to want to keep up with her eyes, and pretty soon her whole body will feel as if it's turning, but of course it really isn't. Orbiting laboratories play a vital part in allowing astronauts to investigate the mysteries of the human body. Space research may one day help solve the puzzles of earthbound problems such as heart disease, osteoporosis, and other disorders. The possibilities are as limitless as the stars. This is a spacecraft. It's also a space laboratory. Located in the cargo bay of the orbiter, the Space Lab is used to study things like biology and the processing of new materials. On this flight, the lab is being used to study how spaceflight affects the body. The difference between space labs and Earth-bound laboratories is microgravity. Microgravity is the result of being in a free-fall orbit around the Earth. Freefall makes things appear to float when they're actually falling. In space, microgravity can affect the cardiovascular system, the heart arteries and veins. We know the cardiovascular system becomes weaker in microgravity. It's called deconditioning, and it can reduce the astronaut's exercise capacity during flight. In a replica of the Space Lab on Earth, scientists devised a specific set of instructions for the astronaut to follow in flight. In order to gather the necessary data, the experiment had to be performed firstly on the ground, during the flight, and after landing back on Earth. The instructions ensured the experiment was carried out the same way each time, enabling the scientists to make accurate comparisons. Another vital piece of equipment on board the spacecraft is the General Purpose Workstation. It provides a shield between the astronauts and potentially harmful substances like fumes and toxic materials. It also provides a container for items that would simply float away if the General Purpose Workstation weren't there, like water. Look how well it works. For safety reasons, any liquid that's spilt must be soaked up immediately. In space, it could float around and short-circuit a piece of electrical equipment. So, thoroughly cleaning the General Purpose Workstation is a safety must.
Why, some say the moon. Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
That brings us to the end of this edition. We look forward to your company next time. But remember, we are out there. What we can and can't see is out there, and the mysteries between us, although seemingly insurmountable, are encompassed by a disappearing frontier.